Morning everyone, I'm Uma Maheshwari, Assistant Professor, Department of Electronics and Communication Engineering. In this video lecture series, I'm going to explain about quadrature amplitude modulation. Call it as a QAM. It is a form of modulation which is widely used for modulating data signals onto a carrier used for radio communications. QAM is a signal in which two carriers shifted in phase by 90 degrees which are modulated. The resultant output here consists of both amplitude and the phase variations. Hence, it may also be considered as a mixture of both amplitude and the phase modulation. The QAM is mainly used to save the bandwidth. How this is even suppressed a carrier which occupies twice the bandwidth of the modulating signal. This is very useful for the available frequency spectrum. It places two independent double sideband suppressed carrier signals in the same spectrum as one ordinary double sideband suppressed carrier signal. The, it exists in both analog and the digital formats. The analog versions of QAM are typically used to allow multiple analog signals to be carried on a single carrier. It combines phase modulation and amplitude modulation in a form of modulation known as a QAM. In the basic way in which a QAM signal can be generated is to generate two signals that are 90-degree out of phase with each other and then sum them. This will generate a signal that is the sum of both ways which has a certain amplitude resulting from the sum of both signals and a phase which again is dependent upon the sum of the signals. There are two RF carriers that can be modulated. These are referred to as in phase and quadrature signals. The I and Q signals can be represented as I which is equal to A cos of phi and Q which is equal to A sin of phi. It can be seen that the I and Q components are represented as cosine and sine. This is because the two signals are 90-degree out of phase with one another. QAM modulator. Here it is mainly used to encode the signal, often data, onto the radio frequency carrier that is to be transmitted. The QAM modulator essentially follows the idea that can be seen from the basic QAM theory, where there are two carrier signals with a phase shift of 90 degrees between them. These are then amplitude modulated with the two data streams known as I, that is in phase, and the Q or the quadrature data streams. This is nothing but the diagrammatic representation of the QAM modulator, where the input is given to the mixture and then to the oscillator and the 90-degree phase shifter, and then the mixture again, the both mixture gives here the output. Here the two resultant signals are summed and then processed as required in the RF signal chain, typically converting them in frequency to the required final frequency and amplifying them as required. It is worth noting that as the amplitude of the signal varies any RF amplifiers, that must be linear to preserve the integrity of the signal. Any nonlinearities will alter the relative levels of the signals and alter the phase difference, thereby distorting the signal and introducing the possibility of the data errors. QAM demodulator. It is very much the reverse of the QAM modulator. The signals enter the system. They are split and each side is applied to a mixture. One half has the in-phase local oscillator applied and the other phase has the quadrature signal applied. Then QAM demodulator. Here the input is given to the splitter which splits and gives the input to the mixtures, then finally to the oscillator and the 90-degree phase shifter and will get us a in phase output and the quadrature phase output. Here will in QAM the constellation diagram which plays a major role. It shows the different positions for the states within different forms of QAM. As the order of the modulation increases, so does the number of points on the quadrature amplitude modulation, which is shown in the constellation diagram. The main advantages of a QAM is using this, it is a higher order form of modulation. Then as a result, it is able to carry more bits of information per symbol. By selecting a higher order format of a QAM, the data rate of a link can be increased. The main advantages here is bandwidth efficiency. Transmit two signals, each of bandwidth B at 2B. More data can be transferred. Bit rate is increased without increasing the bandwidth by increasing the value of M. If data rates beyond those offered by 8 PXK are required, It is more usual to move to QAM since it achieves a greater distance between adjacent points in the IQ plane by distributing the points more evenly. Then the main disadvantage of it is it requires coherent demodulation with exact phase and the frequency. The main application of this QAM is it is used in ADSL technology for copper twisted pairs whose constellation size goes up to 32768 QAM. Ultra high capacity microwave buccal systems also uses this. And for domestic broadcast applications, 64 and 256 QAM are often used in digital cable television and cable modem applications. These are the assessment. Thank you.